Hello everyone, my name is Prannoy and today I'm with my collaborators Alkesh and Christian. Today we're going to talk about a final project for the course ENPM 809K. Next slide please. The problem which we were working on for the past 1 month is online planning for multi-agent systems. Online planning is a hot topic among motion planning enthusiasts for the past 10 to 15 years. Traditional online planners include solving the problem by replanning the system whenever the robot is faced by an obstacle or is about to crash with an obstacle. So this process is very computationally expensive as the robot needs to replan for every obstacle it has faced. And this problem only gets worse once you consider the curse of dimensionality for multi-agent systems. The aim of our project is to understand how deep learning can solve this issue and elevate the curse of dimensionality when dealing with multi-agent systems. Next slide, please. So this is an example of how curse of dimensionality is affecting the system. So as you can see, the figure in left is a one-dimensional path for a robot where the robot walks in one straight line. The figure in the middle is for a dimensional space of n equal to 2, and the positions are now varied over a plane, and there are a lot of positions which the robot can take now. And when you increase the dimensionality to 3, the possibility of positions for the robot just explodes. And when you consider an n is equal to 1000 space, which is common for a multi-agent system, and the states of the systems are just endless. Next slide, please. So these are some related works in the space of online path planning. So the first example is work by Nieto et al., which implements online path planning by using RRT star. RRT. The process is pretty similar to the one I explained before, where the replan for every time the robot encounters an obstacle. The only advantage is using RRT, which is a faster process compared to other heuristic based methods which are out there. So the more recent works from Sung et al. Is on the training of neural network for online path planning with offline path planning algorithms. In this work, they implement neural networks and use uh, two path planning algorithms for their data set and train a neural network based on that. So the path planners they've used is for continuous action space, and this poses some kind of suboptimality uh, when training the algorithm and with its result. And the state of the art when it comes to online path planners is Primal from Sartoetti et al. So Primal is a deep reinforcement learning based planner which trains the model to learn from thousands of robots. And whenever the agent is stuck, it uses an expert planner to elevate the problem and learn from the expert planner so that it doesn't repeat the mistake again. Next slide, please. So this is a schematic of a working diagram. The blue triangle is a schematic of a vehicle, and the green concentric circle is a goal. The black circle is our obstacle. Next slide. So from that, we can extract the features this way. The angle between the goal point and the vehicle's position is angle towards goal, that is AG. The angle between obstacle and the vehicle is AOBS, that is angle of obstacle. And then DOBS is the distance between the vehicle and the obstacle's closest point. So now Alkesh will take over.
Hey, my name is Alkesh, and I'll be talking about the technical challenges that we faced when we were generating this model. Now, the first problem that we faced was generating the data. The model that we preferred, the base that we decided to work on was based on continuous time space. And it required, as you can see on the screen, like three different features, which is the distance of the obstacle, the angle of the obstacle, and the angles to the goal with respect to the vehicle. So the major problem that we faced was that we didn't have the data for a discrete time space problem. The thing is, we decided to reduce the problem to a discrete to understand the optimal nature of such planners. So we decided that we'll be using A star and RRT star to generate the data set. This was partly because A star is an algorithm that focuses on the optimality uh, of the graph search of the graph traversal space. So to deal with that, we created a discrete but dynamic environment of 300 by 400 grid size with a circular obstacle of radius 35 units that moves randomly. So our approach was, as Prannoy explained what these means, start, goal, and obstacle. Our approach was to have randomly place start position, goal position, and the obstacle position. So we moved them randomly here and there, and then planned some path using the RRT and A star algorithms. We were able to get the say that one plan is generating like if one plan is generating an output that has L different points, discrete points, then we were able to extrapolate using that. And we were able to harness these three features using those points. And from like 10,000 path that we found using this method, we were able to extrapolate around 1.9 million data points through which we were able to train a neural network. The second challenge that we faced was finding a correct architecture. So instead of randomly placing different layers and working on randomly, we decided to have a very systematic approach. So the reference that we use for this project use a 3-layer 50 neuron structure. Pretty simple, pretty straightforward. Would have taken like very less time to train. But since this was now reduced to a discrete time space, this model was failing. So we decided that instead of using a continuous time space, we'll be using an action set that includes of 8 different directions: up, down, left, right, up, right, down, left, down, right. So these 8 things almost cover the 360 degrees of a robot that should move in 360-degree dimensions, 360 degrees of direction. Then these were sufficient to cover them all. So we tried to do that. And when we did the data analysis, then we found that, as you can see over here, just take any of thing like say a obstacle or a goal. You'll see that the 6th and the 7th step, which according to this is down left and down right, as you'll see that both of them have closely related values. And this poses a very great problem to the classifier, because this time it is a classifier, not a regressor, because we are planning to classify them into 8 different classes. So therefore, we saw that this is getting very difficult. And so this approach that we took was, instead of classifying them into down, left, down, right, why not club them to a single thing and reduce our action set to 4 steps, 4 action sets, like up, down, left, and right. If it's moving down left, or if it's moving down right, it's definitely moving down. This actually helped. We thought that this might increase the problem, but this actually helped. And as you can see, it's pretty easy to classify these separately. Now the problem seems more simpler. The distribution seems more, uniform, and this actually helped our neural network to gain good accuracies. So yeah, that was our solution, to reduce from 8 action sets to 4 action sets, which proved very effective. Now, to find the correct architecture, we took a very systematic approach. As I mentioned, that we started with single layer and we increased the number of neurons in them at the exponentially with base 2. So we started with 2 to the power 0, and then increased it up till 2 to the power of 15. So we had from like 0 to whatever 2 to the power 15 amounts to. So as you can see, for 3-layer structure over here, it starts at 2 from 0. So 2 to the power of 1 is 1, 2 to the power 0 is 1. So it starts at 1 and then slowly increases. The accuracy, the loss for training and validation is plotted here. And there's a sweet spot right in the mid, and that is 512. So for 3 layers architecture, 512 neurons were the best structure that could give us good results. We did the same for 4 layers, and we found that at 128, with 4-layer architecture, with 128 neurons, it was performing good. And after that, it was converging. So, 3 layers, 512, and 4 times 128, 4 times 128 seemed a more computationally feasible option. And we decided to stick with that. Another reason for that was the fact that if we look at the training curves, then you'll see that with each increasing epochs, this is just for 10 epochs, but it happened for larger epochs as well. The thing which is supposed to go up, that is the accuracy, is going up, and the thing which is supposed to go down, that is the loss, is going down. So 4 times 128, that is 4 layers of 128 neurons, seem to be the perfect, for the given data set that we had generated ourselves. This seemed to be a proper answer to the questions that we were trying to tackle. So these were the two technical challenges that were based on the architecture. The third one was the bias of the output. We realized that even if we are having the same number of class, even if for each class we have equal number of training examples, your output can have a bias. This was partly because since I mentioned that we extrapolated these data points from a single path, so we had more data points that accounted for distances that were small. So what we decided that we'll clip those distances and we'll just try to equalize each of the training samples feature. This actually helped. So for the first case that I mentioned where we were not clipping anything, in that you will see over here that the output, which is the first step, was only and only depending on goal. This is the correlation matrix, the correlation graph. So the redness, no matter if it is more red, then there is more correlation. So this angle of goal, the first step was only dependent on angle of goal. This signifies that if we did not have obstacle readings, both distance and angles, even in that case, it would have performed similarly, which was a bad thing. So as soon as we clipped it, we found a very interesting answer to the question. Now you'll see two very interesting observations. Now we have, yes, from zero, we have some correlation now. Now the output depends on the distance of the obstacle and the angle, the heading it makes with the goal. So this makes sense because you need to avoid the obstacle and at the same time move towards the goal. There's very interesting observation over here that now we have a gray area, and that's the negative correlation. This negative correlation is something that's really interesting. So this negative correlation is between the angle the vehicle makes with the goal and the angle the vehicle makes with the obstacle. They are negatively correlated. That means your robot, your vehicle should avoid the obstacle, should move, face away from the obstacle and face towards the goal. This is something that I found that this was in accordance with the real world. And this signifies that our data was correct. And it was partly because we used A star and RRT stars for our data. And we were moving in the right direction. This was the first step that we realized that, yeah, this is something that we should keep in mind, and we will be getting good results from that. And we got. And Christian will tell you what result we had, and he will take over from here.
Hello, Alkesh. So yes, thank you. Well, I'm going to explain you about the results that we achieved with this project. Basically, as you can see in this graph, we have a 4-layer 128 neurons. As Alkesh presented, this is the best model that we could consider. And the first thing that I want to point between these two models is how we were able to close the gap in between the loss and accuracy. The gap that a couple of slides before he was pointing that it was a big gap. With these layers and this number of neurons, we were able to close this gap and find at least a merging point. The loss gets as the loss decreases drastically up to 30 epochs, and then it starts to converge into about 0.65, if I'm not mistaken, and then the accuracy starts raising and converge up to 0.68. For multiple reasons, we consider this as a good result, because we also consider the idea of how the model has been trained. To this, I'm going to explain this scenario that we have found very, very practical for our decision. So imagine that we have an obstacle in front of us, and we are the car on the south trying to avoid this obstacle. So logically, we can either choose right or left directions to avoid this obstacle. And this basically gives two possibilities, at least two possibilities on a model, and can be trained. Because of this idea, because of this concept, the model achieving an accuracy higher than 0.5 it is considered a good result. Because of the tendency that this model has to have multiple options that could take you to and lead you to the right results, we cannot determine just one single path, because then we could get into overfitting and then we can completely ruin our model. So going back to our training results, another thing that is worth to mention is the number of epochs that we actually achieve this merge, and how the steep of these graphs are not increasing drastically anymore. We can say that about 40 and 50 epochs we have achieved a good amount of data, and our results are clearly enough to be a fast model. So now to show how our model is performing, I'm going to present a video, which is going to start our starting point is going to be in 0, 0, and we're going to try to reach this dot behind the red circle. And as you can see in this video, the model tends to go to the right and then goes upper. And as we mentioned before, another solution will be go up and then right. The straight line, we can explain this because, as Alkesh mentioned before, we were able to reduce our motions, and therefore get a better accuracy and a better model. This also limited us to have sharp angles and not go around the circle as close as possible. Will be minimize the time, but by doing this, we will create a very complicated model. One more time, in this video, you can see how the model successfully avoid the obstacle and reaches to our desired location. So to conclude, as far as a broader impact, we have also selected that a non-hologram action space, such as use of Durbin curves, can be utilized in the future. This means that instead of going into 4 defined options or actions that we can take, we can increase these and therefore get closer to the circle or get closer to the obstacle to achieve a better path and a faster speed of converge. Also, we have determined that a better work can be done to reach a higher accuracy and account for optimality. This will be achieved in the case that we get better data. As we mentioned before, most of our data was generated. So if we have more models that perform better and we get better data, this model could improve. Additionally, this model takes into account one obstacle. However, this could be extended to multiple obstacles or dynamic obstacles. Our model, it's only showing the static obstacle, but yeah, as a future progress, we can do dynamic obstacles, which is something that requires more computational power. And as our deep learning is rarely used for motion planning, partly due to the mature enough to deal with varied complexities. As we explained before, we have several things that we have to consider to analyze this model and to train this model. And for this reason, we have considered 73% of accuracy as a feasible model that it's gonna convert faster. Thank you. That will be everything for this project.